Because you're watching this video, thanks. So we're going to look at specific volume formula for a two-phase mixture. In the previous video, we covered some of the terminologies we use in thermodynamics. So in case you didn't watch that video, you want to check it so as you get to know the terminology, some of the terminologies that are used in thermodynamics. So, specific volume formula for a two-phase mixture. What's a two-phase mixture? A two-phase mixture is a mixture that's divided between vapor and liquid. It has two states, two phases. Okay, and in detail later in another video we shall go in detail and understanding what a two-phase mixture is. So in future, I plan on making a detailed video for you on understanding what a phase mixture is. And by definition in physics, specific volume is represented by a small case v. This is v not u. Small case v, and it's the total volume divided by mass, a specific volume. And density is represented by a Greek letter mu, which is equal to total mass divided by total volume. Well, you just said density is mass per unit volume. And total volume is represented by a capital V, which is equal to mass divided by density. Volume is equal to mass by unit by density. So if you relate these two here, you're going to get specific volume is equal to volume substitute for volume, which is mass per density, so which is mass, and we have an m here. So once you divide, you get 1 over log as the formula for specific volume. So yeah, you need to master those formulas and have them in your head. And it's quite a simple one. You just have to know that specific volume you're dividing by mass. Actually, it will work for everything. Every time you hear specific density, specific entropy, specific enthalpy, you just have to divide by mass of the property we're defining. So now we have a liquid vapor system. This is a phase system where liquid water and water vapor are in equilibrium. So to illustrate this, you have maybe a electric kettle that has water and it's boiling. It's boiling, it has vapor, when water is boiling, it is evaporating. So it has vapor, and as it's evaporating, the water didn't vanish, there's still water. So it has liquid water and water vapor. And because though these are two different phases, they all share the same pressure because the pressure from the walls of the container and from the atmosphere is all equal, so at the same temperature. But because the two phases do have different volumes, there'll be that volume that is occupied by the liquid and that volume is occupied by the vapor. We shall look at that in detail throughout the video. So here you will look at us use this subscript F and you ask yourself why F. So much of this physics was developed by people in Germany, the physicists in Germany, and they got to name the stuff in their language and after themselves. So F is a German derived subscript for, I don't know how to read this word, but it translates for liquid. So when we have lowercase v subscript f, it translates for volume per unit mass of saturated liquid. So liquid instead of L representing with Fy because it is gotten from this great German word which means liquid. And lowercase v subscript G translates for volume per unit mass of saturated vapor. or gas, vapor is gas. That's why we have G. And mass subscript F is mass of saturated liquid phase in mixture. And this is mass of saturated vapor phase in mixture. And anytime you look at us use X thermodynamics, we're not talking about a known X, Y. No, that's for mathematics. Here we talk about quality concept. The quality concept is represented by X. We shall look in detail what these mean later. So to understand this entire thing and derivation, you need to know something called total volume. So consider a rigid tongue or simply uh, electric kettle. So it is containing liquid water and water vapor, some liquid, some liquid water and some vapor. So if total mass of, so you want to write this, and these are the conditions you state before you derive the whole formula of specific volume. So if the total mass of the mixture is equal to M, total volume of container is equal to V. So it is the condition you want to first assume, consider tank containing liquid water and water vapor, i.e. some liquid water and some vapor. Total volume of container is equal to V, but the actual quantity of liquid versus vapor is not known. Remember, you put at the start of the whole process, you heard an electric kettle of defined rigid. Rigid means its volume does not change, rigid tank or rigid kettle. It does not change, its volume does not change. So you put in a given amount of water, right? And then you boil it. So as it says boiling at 100 degrees Celsius, you no longer know the volume of the water because some of it is evaporated and is now in the vapor phase. So now you can no longer know the actual quantity of liquid and that of vapor. Thus, you can, however, know that the total volume of whatever is inside the electric kettle is equal to the volume of the liquid phase, the water which is still liquid, plus the volume of the water that has transitioned into vapor, which is volume of the vapor phase. And you are not going to keep writing liquid and vapor. You are going to use the subscript F and G to show vapor and liquid. So from specific volume, lowercase v, we already stated it that lowercase v is equal to capital V divided by M. So you make volume subject to the formula and you have V by M. So now we want to substitute into this formula. So volume of the liquid phase is equal to mass of the liquid phase by specific volume. Please to note there that lowercase v stands for specific volume. So total volume of the liquid phase is equal to mass of the liquid phase by specific volume of the liquid phase. And the same with the vapor phase. So once you substitute in this formula here, you're going to get this, and you encourage to put the curly blades to for easy solving. So this is a mathematical writing, and you can translate it in English as total volume, which is V, is equal to mass of the liquid multiplied by its specific volume plus mass of the vapor multiplied by its specific volume. So from total mass. So now the same analogy works. Since you cannot know the volume of occupied by the liquid and the vapor, you also don't know its mass. But you for sure do know that the total mass of the two is mass of the liquid phase plus the mass of the vapor phase. So you can say total volume M is equal to mass of the vapor phase plus mass of the liquid phase. So we now want to bring this quality concept. I told we looked at it at the beginning of the video somewhere here. We said X is the quality concept. So you want to introduce it and you say X is equal to mass of the vapor phase divided by total volume, by total mass, sorry, total mass. Now you make mass of the circulated vapor as the substitutive formula and you get X by M. So from this here, you come to this. Total mass minus mass of the vapor phase, you get mass of the liquid phase. So now, but we already know the mass of the vapor phase is equal to Xm. So you substitute it in here. I would encourage you to do this on paper by yourself, like redo it. It will become more easy and easy to memorize. Okay, you can follow along and to understand why we did substitute why at a specific state, but it's also encourageable and a good practice for you to get a paper and you write along and solve the equation. So we substitute for mg here, right here, from this state, and we we're going to move m out, so we get 1 minus x, and we'll bring m out. And now we're going to substitute whatever we have got into our formula, this formula here. And it will look like this once you've finished solving. And you bring the m out again, and you get this. But we're not finished yet. We know that specific volume is equal to total volume by m. So now once we divide by m here and here, we're going to get specific volume, which is equal to 1 minus x into specific volume of the liquid phase plus a quality concept into specific volume of the vapor phase. And this here is the two-phase mixture formula. So I would encourage you to get a paper and you go through it again. It's a very simple thing once you look at it for the first time, because it's how many lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. But it can be really hard if you take it for granted. So this is a two-phase mixture formula. In the next video, we shall look at the interpretation of the two-phase mixture formula. We shall interpret what this means. So check out our next video in the playlist we have created by visiting our UPO, visit our the video description and bio in the video, and you check the entire video out to keep track of the thermodynamics. And thank you for watching.